Hello everyone. So welcome to the second lecture of Organic Chemistry Fundamentals. In the previous lecture we were discussing about drawing Lewis structure for various molecules, and I gave you a little homework, that is to draw the Lewis structure for these four molecules. Now let's just go through the answer part. Now for HNO3, one thing is for sure, if you have never seen the HNO3 molecule structure before, then you will be making a lot of mistakes at first, right? So it is important that you must try all the different arrangements, and then when you look at the answer, then you identify what mistakes you made. Okay, what kind of wrong connections you made. For example, in HNO3, while making the bonds, let's calculate the valency of hydrogen plus nitrogen plus 3 oxygen. So hydrogen has 1 valence electron, nitrogen has total of 5 valence electrons, and 3 oxygen has total of 18 valence electrons, right? So we have total 24. So 24 electrons we have to organize in the form of bond pairs or lone pairs. Now one thing, the most connected atom, the one that makes most number of bonds among hydrogen, nitrogen and oxygen is the nitrogen, because nitrogen normally forms 3 bonds and keeps 1 pair of electron. So the idea is to keep the nitrogen in the middle. So let's put the nitrogen in the middle, and hydrogen is always at the periphery. So let's just connect the hydrogen here and let's see how it goes. Now we have to organize or arrange 3 oxygens. Now you cannot make 3 bonds with the oxygen. You can make maximum 2 more bonds with nitrogen. And if you make something like this, then it will be wrong. Why? Because nitrogen has 3 bonds and 1 lone pair. Okay, so we had to use 24 electrons, that is 12 pair of electrons. So 1 pair, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Done. Still hydrogen has its duplet, because hydrogen doesn't get the octet, it gets a duplet. But this oxygen will not get a complete octet. Secondly, single bond between oxygen and oxygen in this way, first of all, it doesn't complete the octet of this oxygen. Secondly, it's not a very strong bond. So we have to avoid making such connections where the octet is not complete. So second, we can try one more structure. We can add oxygen in between the hydrogen and nitrogen. Now the remaining 2 oxygens we can connect like this, right? Now we have to arrange. Okay, so how many pair of electrons we have used so far? 1, 2, 3, 4. So we have to use 8 more pair of electrons. So we use 2, 3, 4, 5, 6, or let's say 7. 1 more. If you give it here to oxygen, then the nitrogen will not get a complete octet. If you give it to nitrogen, this oxygen will not get a complete octet. So you make a double bond. So both nitrogen and oxygen will get a complete octet. Now the nitrogen already has 4 bonds. So it must be, or you can say that this one must be a coordinate bond, because this oxygen has not used any of its electrons in the bonding. All 6 valence electrons of this oxygen have been kept with the same atom. It has not used any of the electron in the sharing. So this bond from the nitrogen to oxygen must be a coordinate bond where both electrons are given by the one atom. Okay, nitrogen gives both electrons for this bonding. So this is the Lewis structures for HNO3. Clear? Second is carbon monoxide. So carbon monoxide, so carbon has total 4 valence electrons, oxygen has 6. So we get 10 electrons, that is we get 5 pairs. So carbon, oxygen, let's put it like this: 2, 4, 5, 6, 7, 8, and let's say 9, 10. Now in this case, the carbon doesn't get a complete octet. Second time, we try like this: 2, 4, 6, 8, 10. Here the oxygen doesn't get a complete octet, so they are not stable arrangements. So next we can try something like this. So the carbon, so we have total 3, 4, 5 pair of electrons. The carbon gets a complete octet as well as the oxygen gets a complete octet. So that's the right Lewis structure for carbon monoxide. It was fairly easy. Then for nitrogen, the nitrogen has 5 valence electrons and 2 oxygen will get 12 valence electrons. So 12 we have 17 electrons. Now 17 electrons cannot make all electrons paired. Maximum you can have 8 pairs plus 1 additional electron. So it will be an odd electron species because we don't have even number of electrons so that we can pair them all. Now in this case, keeping the nitrogen in the middle because nitrogen forms more number of bonds compared to oxygen. It forms 3 bonds. So 1 oxygen here, 1 oxygen here, like that. And total we have to use 8 pair. 1, 2, let's say 3, 4, 5, 6, 7, 8. Still one more electron left. So we can keep this electron on nitrogen. Right? And if you have gone through the chemical bonding chapter, which you might have, then you know that it will be a bent structure. Okay? Because of the Vesper theory, it will be a bent structure. So this is the right structure if you want to indicate the bond angles, the correct geometry. But if you just want to write or draw the correct Lewis structure, then this is fine. Then comes the HCN. So for HCN, you can practice, or you might have drawn it in the junior classes also. This is the Lewis structure for HCN. Now the thing is, drawing Lewis structures is one thing, but don't think that it's a very, very important phenomena. You just need to understand the way atoms connect in different molecules. Where to put the oxygen, where not to put the oxygen, how to use nitrogen in the bonding. So next we are going to discuss the bonding pattern of boron, carbon, nitrogen, oxygen and halogen. And this will also include a little information about the formal charge, or we can use the same diagram while explaining the formal charge also. Now, I'll start with the boron. So boron has a valence of 3 electrons. So let's use all 3 for bonding. So from 3 valence electrons, it can maximum form 3 sigma bonds. That gives it 6 electrons. Still octet not complete. Right? Then we go to carbon. Carbon has 4 electrons. So from 4 electrons, it can make 4 bonds. One option, it can make 4 single bonds. Second, it can make 1 double bond and 2 single. Third, it can make 1 triple bond and 1 single. So total it has to make 4 bonds in order to complete its octet. Now there are these 3 possibilities, and there can be one more possibility which is not very common, but yes, you cannot ignore it. Making 2 double bonds. Right? 4 single, 1 double, 2 single, 1 triple, 1 single and 2 double bond. So these are the bonding patterns of carbon. Then you go to nitrogen. Nitrogen has 5 electrons, but nitrogen doesn't form 5 bonds like this. Why? Because if it does, then nitrogen will have 10 electrons in its octet. It cannot exceed the octet because it doesn't have the empty d orbitals. So you cannot draw 5 bonds for a nitrogen. So how about drawing 4 bonds? Let's say I draw 4 bonds. So in this I have utilized 4 electrons. Fifth will be left over. 4 bonds means total 8 electrons, because we are also counting the shared one. Every bond is actually 2 electrons. So 8 electrons from the 4 bonds plus this additional. Again octet is exceeded, 9 electrons. So 4 bonds arrangement is also not stable for a neutral nitrogen structure. So the trick is, the nitrogen will form only 3 bonds and keep 1 pair of electron. So it utilized 3 of its valence electrons in bonding and kept 1 as a pair. So now the octet is complete and everything is just fine. Second thing is, if you have to draw 3 bonds, then it can be 3 single, 1 double, 1 single, or 1 triple. So these 3 bonding patterns can be found. Then let's talk about oxygen. Oxygen has 6 valence electrons. So it will form 2 bonds and keep 2 as pair, because if it forms 3 bonds, so 1, 2, 3, 3 electrons utilized, 4, 5, 6. So now it will have 2, 4, 6, 8, 9. 9 electrons, octet exceeded. So that is why oxygen will only form 2 bonds. So it can have 2 single bonds or it can have 1 double bond. So that is the bonding pattern of oxygen. So wherever you see oxygen in the bonded arrangement, you will always notice that almost always either oxygen form 2 single bond with 2 lone pair or 1 double bond with 2 lone pair. And halogen, because it just requires 1 additional electron to complete its octet, it will form only 1 bond and keep 3 pair of electrons. Now, okay, you'll say that we already know this, it's not a big thing. Yeah, but what I'm trying to tell is not how they make bond or how many bonds each one of them is making, but how the bonding is irrespective or it is independent of the identity of the atom. For example, when the carbon had 4 electrons, it made 4 bonds, 4 single, 1 double, 2 single, 1 triple, 1 single, or 2 double. Now, let's take the example of nitrogen with a positive charge. Nitrogen normally has 5 valence electron. If it loses one of them, it will have only 4. When it has only 4, then it is just like carbon, because carbon also has 4 electrons for the bonding. Now, N positive also has 4 electrons for bonding. So the kind of bonding that we experienced or that we studied for carbon is same for N positive. Look how similar they are. Why? Because this has 4 electrons and this one also has 4 electrons. Now let's talk about nitrogen. Nitrogen in the neutral state has 5 valence electrons. Oxygen has 6. So if you take O positive, it also has 5 electrons. So O positive has similar bonding arrangements as that of nitrogen. Just that oxygen normally doesn't form a triple bond. Then let's take the example of carbon and boron. If carbon loses 1 electron, it will have 3 valence electrons. Then its arrangement will be just like boron. 3 bonds. Either 3 single, 1 double, 1 single, or 1 triple. That's all. So that's what I'm trying to tell you, that bonding arrangements don't depend on the identity of metal. They depend on the number of valence electrons which are available for bonding. Similarly, you can also understand the bonding when they have 1 additional. When carbon gains an extra electron, now it has 5 electrons. So here the bonding arrangement will be just like nitrogen, because nitrogen in the neutral state had 5, carbon in the negative charge state has 5. So similar arrangements. Okay, so I think that much is sufficient for this lecture. For the next lecture, here's small question for you. Write down the Lewis structure for each of the following. Okay, I'll just give you the answer in the next lecture, and then we will move on to the calculation of formal charge. Okay, so if you like this video lecture, please share it among your friends, because we need your support to continue making such lecture series. And yeah, we can make a big impact if you students decide to support us. Okay, so stay healthy, have a nice day. Thank you.